Here's another problem from that supplement to the final exam review, which is the practice problems for the final exam. Again, not an inclusive set of problems. Or what I mean by that is the practice problems on their own will not adequately prepare you for the final exam. Just so you know, I was not being careful about covering all topics in that set of practice problems. I just want to keep putting that disclaimer out there. But the final exam review, that will cover all topics. All right, question 5b. So we're given a subset W of R3. In this case, W contains vectors of the form A minus 2B, A plus B, 3A plus 4B, where A and B are just any real numbers. The theorem that really helps us answer this question is this one, which says the span of a collection of vectors within a vector space V is a subspace of V. The reason for that, by the way, so the justification of this theorem is, okay, so let's say we have, here's our vector space V. So we already know that V satisfies those 10 axioms of the vector space. I'm going to say let's take like 3 of those vectors, and just 3's random number here. But so suppose we take the span of a few particular vectors within that vector space. So is the span of those vectors a subspace? Let's say these are U, V, and W. So span, remember, is a set of all linear combinations. A subset of a vector space is itself a vector space. It's called a subspace if it satisfies 3 requirements. So we go from the 10 axioms down to just 3 that we have to check when we know we're dealing with a subset of a vector space. So that subset is a subspace, meaning it's a vector space on its own, if it contains the 0 vector, it's closed under addition, it's closed under scalar multiplication. If we're talking about a span of particular vectors in V, first of all, it's automatically, that span will always include the 0 vector, because we would just take 0 times every vector. And, scalar multiple, where the scalar is 0. Then that's always going to generate the 0 vector. So yes, it contains the 0 vector. Closed under addition and scalar multiplication, sure. I mean, that's what span is. The span of, so for what I've drawn here, U, V, and W, is the set of all linear combinations of U, V, and W. So it's the set of all vectors of the form some scalar times U plus some scalar, let's say B, times V plus some scalar times W. All vectors of that form. So as I said earlier, it contains the 0 vector, sure, just let A, B, and C all equal 0. Closed under addition, sure. Yeah, I mean, if A and B are, let's say, 1, then the sum A plus, or U plus V is going to be in there. Here, you take any 2 vectors that are in the span, add them together, you're going to get another vector of this form. That's what I should say. And scalar multiplication, sure. I mean, both of those kind of go without saying, just by virtue of what a span is. It's automatically going to contain all the sums and all the scalar multiples, because that's what we're talking about when we talk about all linear combinations. Okay, so that's the argument behind this theorem. I'm probably giving you more than you wanted to hear. Again. So this particular set, the idea is if you're given a subset that you can easily express as a span of vectors within the vector space, then you invoke this theorem and you're done. Okay, so the real way you work this is you say, okay, any element of this set can be expressed as A times the vector 1, 1, 3 plus B times the vector negative 2, 1, 4. Again, where A and B are any real numbers, which means this set W can be expressed as the span of these vectors 1, 1, 3, negative 2, 1, 4, which are 2 vectors in R3. So this right here proves that W then is a subspace of R3. The vector space V in this case is R3. And the answer is yes. This is a subspace. W is a subspace, I should say, of R3.